Hello, everyone. Thanks for coming to the Temporal Graph Reading Group today. We are very glad to host Kartik again. So today he'll be presenting his paper, Temporal Dynamics Aware Adversarial Attacks for Discrete-Time Dynamic Graphs, which I believe was also previously at the Temporal Graph workshop last year, right? And so definitely very interesting and exciting work. In terms of a bit more information on Kartik, So Kartik Sharma is a second-year PhD student advised by Prof. Suranjan Kumar at Georgia Tech. Before joining there, he graduated from IIT Delhi in 2021, where he was fortunate to be advised by Prof. Sayan Ranu. His research focuses on learning and optimization for graph structure data. Through his research, his goal is to study the effectiveness of these models in difficult and practical scenarios and develop new models that can circumvent these problems with a theoretical grounding, which ties in very nicely with the work today, actually. And I will hand the mic to you, Kartik.
Hi. Yeah, thank you for inviting me. Yes, I'm actually now a third-year student, so yeah, I would upgrade that. Can you see my screen just to confirm?
Yes, we can see your screen. We can see the audience window, basically.
The audience window, okay. I hope that's the case. Yeah, that's good. Okay. And yes, should I start?
Yes, please go ahead. And do you prefer us to ask questions in between the slides or at the end of the talk?
You can interrupt me anywhere, anytime, and I would be happy to take any questions.
Sounds good. Sounds good. Thanks.
Okay. Okay. So, hi everybody. Thank you for the introduction. I am Kartik from Georgia Tech, and today I'm presenting this work, which was also presented in last year's TGL workshop. But after that, it got accepted in KDD this year, and we also extended. We have some new results and new theories. So I would go deeper into this, and maybe we can have good discussion about what this. And okay, so oops. This is the work. It's titled Temporal Dynamics Aware Adversarial Attacks for Discrete and Dynamic Graphs. And okay, so first going into this, and this is already known, I guess, to everyone in this group, but just still going slightly into it. Brief introduction to discrete time dynamic graphs. One already knows how this dynamic graphs are almost everywhere, and they can model data from a large variety of domains, and almost all kinds of graph data is dynamic, it's evolving, the structure is evolving, the attributes are evolving, and one can some examples are the protein-protein interactions, as which protein is interacting with which protein. That changes with time, and how and this is already studied by chemists and all. And then we also have neural activation patterns or connections between neurons or parts of the brain, and that forms a network, and that keeps evolving over time as the human interacts with different stimuli and all that. And then we also have online social interaction, which is, I think, very well studied as well because of ease in obtaining this kind of data. We are interacting in general every time, and that interaction happens over time and keeps evolving as well. And then similarly, we interact with products on the online forums, and that makes this e-commerce network as well. So yeah, and these are all the dynamic graphs. I mean, this is already probably known to everybody, but just giving a brief introduction. So let's consider this example of temporally evolving social interaction network, where these are humans and they're interacting with texts on the online platforms, and then we also have videos they're interacting, and they interact over time. So let's say at t equals to 0, this is the interaction network, at t equals to 1, this is the interaction network, and so on. And then we have a recommender system, which takes all these snapshots, a sequence of these snapshots, and recommends whether at time equals to 3, the next timestamp, would this boy interact with a video. Let's say that video is explicit content. It contains explicit content, 18 plus, and typically in this scenario, the expectation is that the boy would not be recommended this explicit content in the future timestamp. But if an adversary were to add these perturbations, carefully added perturbations at time equals to 1 and time equals to 2, then the recommendation of the model flips, and the model starts recommending this explicit content to the minor, which is not recommended, which is not expected, which is not desirable in this in any kind of recommendation. And hence, this is a problem. This problem is important to study. We already have a lot of papers on attacks on graph neural networks, static models, but the adversarial attacks which happen over time, and how to construct them, how to evaluate the dynamic graph models on these adversarial attacks is not being studied in the literature as well. And this work, the current work, is an attempt to do so. So just a brief introduction in how the models are, what is this recommender model, how is it learning how is it learning the representations, and from those representations, how is it predicting which link to recommend and which to not. So one such framework is this discrete time dynamic graph, where we assume that we get information at different timestamps, but these timestamps happen over in discrete snapshots. So these are like after every period of time, a fixed period of time, we would sample what is the network right now, and that would form our snapshot. This is in contrast with continuous time graphs, where we are getting the graph information in continuous time over the edges. So as the edges evolve, as the structure evolves, we keep sampling the edges over in a continuous time step. Okay, so we will focus on discrete time dynamic graph for simplicity and for better formulation, but extensions to continuous graphs can also be thought of. I personally do not have much. I personally do not know how to extend the current formulation to continuous time graph, but happy to talk about it.
Mm-hmm. But, and just a quick note about it as well. I think this is very interesting, and couldn't you just first discretize your continuous time graph to some level and then apply your current method on it?
Yes, and I would say also no, because the continuous time graph, I think the granularity is varying, because we can get 100 edges at between time, let's say 12 minus 12 to 0. For example, 11, 12, and 11, 0, we got 100 timestamps, but for the next hour or so, we would get no edge at all. In that kind of like, so we can say that we would sample after every 12 minutes or 12 seconds or some, you can have that sampling time, but the scale of the number of edges that we can handle is still limited. So I guess like since continuous time graphs would have edges coming out very different scales, I don't think our method would be suitable for like such varying scales of number of edges over time. But yeah, I mean, I think that would become clear as I introduce the method. But yeah,
Happy to
I
discuss
will, yeah,
as
I
well.
will come to that. Okay, so for the discrete time graphs, these models are just like sort of, you can think of them as combining graph and sequential learning models. For example, we have GCL-STM, Evolve GCN, and DISAT. These are the three models we consider in this work. And as we can see that all these models are combining GCN, the GNN layers, the graph embedding layers with sequential embedding layers in certain sense. Uh, uh, so in GCL-STM, we first embed the graph snapshots at different timestamps using the GNN module, and then pass those representations through an LSTM module to get these dynamic graph representations at each timestamp. Similarly, while GCN, we do it sequentially, and we get these dynamic graph representations. And for DISAT, we employ the attention modules for both the sequential and graph learning purposes and obtain such representations. So these models are easier to also analyze, I guess, because we can get these A1, A2 to A80. But if we think about it from a continuous time perspective, then it becomes slightly harder to see which edge we are talking about. So yeah. Okay. So yeah, so this is the framework we are dealing with. We have these sequence of graph snapshots. We pass them through a DTDG dynamic, so one of these models that we have discussed, dynamic discrete time dynamic graph model, and we get some prediction. Let's say the prediction is that we do not have any link between the two central nodes at timestamp 3. And now if an adversary were to add these edges, we can flip the prediction. But the argument here is that such an attack, for example, as is shown here, the red edges, is not suitable to study, because if we are studying the vulnerability of these models, we should study these vulnerabilities in terms of perturbations that are actually realistic. But such perturbations, as we have seen in timestamp 2, can be argued to be not realistic, or in another sense perceptible, because we are adding too many edges at timestamp 2, and in some sense we are changing the dynamics too much, and these would be easily detected, and so such an adversary would anyway fail to cause an attack in the real sense, because these perturbations would be perceptible, would be detected by the detectors that we may have in this pipeline. And in more detail, we changed the graph abruptly at timestamp 2. The dynamics was happening in certain sense, and we have changed the dynamics too much. And we would formalize what too much means, but in some sense we have perturbed too much. And even though the prediction still flips, this actually does not say anything much about the vulnerability of the model, because this vulnerability is not something which is realistic. So in the real world. So because this would be detected as an anomalous change in these in the embeddings. Instead, we have this, where let us consider this as an attack where we are adding edges carefully at two different timestamps, not adding a lot of information at any one timestamp, but carefully adding some edges in different timestamps. And one can say that this would also lead to a flip in models prediction. But it can be argued that this is a better test to test the vulnerability of the models against or the robustness of these models if these models are robust or not, because these attacks can be argued to be imperceptible and thus realistic, because these attacks can be argued to be to change the graph while following evolution and would not be detected by other detectors. So here an adversary would actually uh, pass the detector test. So would be successful in making an attack by fooling the detectors, and to also then flip the prediction. So he's able to do both the things, which is great. So yeah, that's the question we are dealing with. And just to reiterate, what we want to do is we want to ask how to formulate the adversarial attacks on the dynamic graphs that can preserve evolution. And to this end, we present a novel constraint on these perturbations, which is the temporal dynamics aware perturbation constraint. And we present a method, an effective method and an efficient method to find these attacks for dynamic graphs using projected gradient descent under this constraint. So yeah, this is the question that we are dealing with, and I would go into more detail. But if there are any questions, feel free to ask now.
Do you have the same concept of basically if you do adversarial attacks a bit too much, like adding too many edges, as you said, in static graph? Is it where the intuition coming from?
So yeah, in static graphs, we would have a budget for each graph, or like we cannot add too many edges. And this is again, this comes from like the budget constraint in images that we should not add too much noise, because too much noise can take away the information that was there in the image. But in this case, when there is dynamics involved, what is too much is actually informed by the dynamics itself. So we don't need to come up with deltas which are arbitrary, but we can we can inform that delta by the dynamics, which is, as the next slide says, which is actually the change, the relative change in the two timestamps, the two consecutive timestamps.
Right.
So that is the intuition, as you rightly pointed out. So the number of perturbations that we can add at any timestamp must be no more than a small fraction of the actual number of changes at that time. So if the graph between t minus 1 and t, if the graph changed by adding by adding like or deleting like 20 edges, then the perturbation should also be limited by a fraction of 20. Should not be, let's say if the fraction is, we set the fraction to be half, then it should not be more than 10. If we add more than 10 edges, then we change the dynamics too much. So that is the intuition. Yeah.
And just one question here. You consider that the set of the nodes are fixed?
Yes, I do. The nodes, or you can say that if there are nodes to be appeared in the future, then actually I would just like in the previous consistency matrices, I would add a row which is 0. So which is all zeros. So yeah, that is correct. Yes.
Thank you.
Okay. So in more illustrative purposes, we have these sequence of graphs, and let us consider the second timestamp. Then we find the difference between the second and the first timestamp. Let's say that is delta A2. Then the adversary would add no more than epsilon times delta A2 perturbations, or can add no more than epsilon times delta A2 perturbations at that timestamp. And similarly, it will add epsilon times delta AT perturbations at each of these timestamps. I think one difference between this and the existing works on extensions of static graph attacks to dynamic graphs is that, which were only two actually, but they were mostly focusing on adversarial attacks, which by constraining the total number of perturbations across all the timestamps. So if we had a budget of 5 or a budget of 10, then that budget can be used in any way across all these timestamps. But what we have is that we can only use a fixed number of, we find a budget for each timestamp. Instead of having a global budget, we have a budget for each timestamp. And that local kind of budget pushes us to more new questions, which we will see later. But yeah, that is the major difference. Are there any questions?
But also, like when you are doing it this way, the objective you are measuring is across all timestamps, or is it also defined basically across individual snapshots? Basically,
Yeah,
the adversarial attack objective.
That's a good question. But so the objective is still across all timestamps, because the objective is prediction at the future timestamp, which is informed by all the previous timestamp. But the constraint is actually at each timestamp.
There could also be arguments where I don't want to go into too much discussion here for the time's sake, but just since I'm talking about this, so you could also like argue that, let's say there's a drastic change between sub snapshots, like you have naturally like, you have some external events that are causing drastic change in the dynamic graph to begin with, and someone who is trying to do a adversarial attack can focus their attack around this time, which people are expecting change anyways, and thus making the embedding being drastically different. You can say that the impact here could also be very significant. So let's say you are expecting higher volume of transactions around Christmas anyways, and now you focus all your attacks around here. So then the embedding you get after that point is significantly divergent from your normal behavior, such that it's impossible for the model to be making correct predictions anymore, because you kind of mask your attacks at the timestamps where there's a huge amount of change.
Yeah, but yeah, so that is actually allowed by our method, right? Because if there are a lot of changes, then but what you're talking about is from the optimization point of view, which timestamp will the attacker actually choose? Will the attacker choose to attack something which is allowed to have more perturbations, or will it choose to do something in the lower perturbation constraint? But yeah, that is true. So we do, I mean, if we have more leeway at a certain timestamp, then the attacker would be tempted to use as many perturbations as possible at that timestamp. Because of course, like more perturbations would definitely help. Because we so from an optimization point of view, he would choose that.
Okay.
But if we do not have these local perturbations or local perturbation constraint, if we had like a global perturbation constraint that you can add any number of edges between any of these, between the whole, instead of just focusing on Christmas, he can add as many edges in the whole year, then he can as well add the perturbations in the start of January instead of at Christmas, to change the prediction for, let's say, February, because there is definitely in the models inductive bias, there is definitely a recency bias that the recent perturbations would be more, recent graphs would be more effective. So any changes in those graphs would definitely be more effective than the changes in the previous timestamps. But our constraint would actually force it to not make any changes, let's say, in the recent graphs, but focus on the those timestamps which actually saw the change in the real data. So yeah,
That makes sense.
yeah,
Thanks.
that's about it. Okay. Moving on, I think so. Such a constraint that I just described have important implications. For example, one, we wanted our attack. We started with that assumption that the attack that we are considering should change the graph while following the evolution. And what we find is the such kind of perturbations that we are studying, for example, would actually preserve the average rate of structural change. That is the average rate of structural change, which is delta AT prime. So once we have attacked each of the timestamps, we can then find the change between the perturbed graphs after the attack, and we find that the average change across all these timestamps remains same before and after the attack. Not same, but like remains bounded. So for example, remains within the bounds of 1 minus 2 epsilon and 2 epsilon kind of bounds. And this is good. So because we are not changing the structural change. So we're not changing the how the graph is evolving. The graph, how the graph was evolving on an average rate before the attack is similar to how it is evolving after the attack. And we also found it's a corollary of the previous result that the rate of embedding change for any embedding, and this here Z can be any embedding model, would also remain same. In fact, we find that the rate of embedding change after the attack remain within bounds of epsilons of how the embeddings were changing before the attack. And this is a direct result of the previous theorem by using Cauchy's lemma. But and you can see the proofs in the paper. But these are very important because now we know that such a perturbation constraint that we propose is actually effective in perturbing the graphs the way we want, and thus it's a good benchmark. It's a good test to test the vulnerability of the dynamic graph models under realistic perturbations. So building upon these, now we want to ask the question that I was discussing with Andy about optimization and how to find these attacks. So the objective, as you can see, is considering all the timestamps from 1 to t minus 1, because using 1 to t minus 1, we would predict the next graph, the edges in the future timestamp. But the perturbations are, or the constraints are actually local. So it's like 80 minus the changes in the local in each graph timestamp in each timestamp t is limited by certain bounds, and these bounds are different for each different timestamp t. So this is the optimization problem we are dealing with, and there can be two different settings which we can study this problem in. And one is the offline setting, where the attacker wants to find these optimal perturbations for all the timestamps. So we get this kind of problem, and now we want to find the AT prime after seeing all the graph snapshots until t minus 1, capital T minus 1. But so this is an easier problem. But there can be another problem, which is an online setting, where the attacker wants to attack in real time. So now the objective is still the same. I should note that the objective is still to make changes or like flip the prediction. Let's say, for example, we want to flip the prediction for February. The objective is still the same, but the perturbations or the perturbations he wants to choose is that he wants to attack in December. To make the perturbations for December, he cannot see the graphs for January. So he sees in the graphs in real time, he has seen the graphs until December, and now he has to make some perturbations for December without seeing the graphs for January, and with the objective of flipping the prediction for February. So he attacks in real time, and once he has made these perturbations, the perturbations for December cannot be revoked. So he makes these perturbations for December, and then the graphs for January comes, and then he has to perturb the graphs for January. So he perturbs in real time. So this is the online setting that we're dealing with. Okay. Any question here? I think the online setting is something which I didn't have earlier in the workshop presentation, but if there are any questions I can take.
So the online basically changes the objective such that the view of the attacker is no longer the entire graph sequence, but just kind of like a subsample time interval, right? If I understand correct.
Yeah, the objective is still the same. It's just that the information that the optimizer has is, or the attacker has, is limited. So the objective is still,
I see.
Yeah, is still to change the future, but he does not have some of the future graphs. He only has the present. So
the online version is theoretically guaranteed to be worse. The optimal solution for the online version is theoretically guaranteed to be worse than the offline one.
Yes. Yeah.
Thanks.
Correct. Okay. Yeah. So both of these, like, online setting and the dynamic evolution aware setting is something which is particular to, or like specific to dynamic graphs, or where we are exploiting that we are dealing with adversarial attacks for dynamic graphs and not static graphs. So that is the distinction, where like these things we cannot have for static graphs, and that is where the novelty and like little contribution comes in. Okay. So the method that we propose is using projected gradient descent. And here we call that the method temporal dynamics aware projected gradient descent, or TDBGD. And it's based on the result that a simple projection operator actually exists for our perturbation constraint. So what a projection operator does is that given any point in the real world, in the real domain, are, let's say, the space of any adjacency matrix, it projects that adjacency matrix to a body of solutions which actually satisfy the constraint. So the closest, and it projects in the sense that it gives the closest point in this body of the satisfiable solutions, which is closest to the point of to any point in the space. So what we get is that we can find the closest adjacency matrix which would satisfy the closest sequence of adjacency matrix, because we are dealing with dynamic graphs that satisfy the TDAP solution, TDAP constraint that we have proposed, instead of giving like any random adjacency matrix which would satisfy. So we would satisfy the closest one. We would find the closest one. And why the closest one is important is because we can then use this PGD approach, projected gradient descent approach, where we take alternatively two steps. We first take gradient step to maximize our loss, which is to maximize the adversarial loss of flipping the prediction, and then we project. And we keep doing this for n iterations, and at the end of that, we randomly round this continuous vector to a solution such that the constraint will be satisfied. But what is important here is that we from theoretical guarantees, we know that such an alternative strategy of taking gradient and then projecting is optimal, or it gives like the optimal solution, suboptimal solutions with a certain guarantee. Or the solution obtained by this is not too far from the optimal of that would satisfy the constraint and would also flip the prediction.
Okay. A quick question here. So is it true that if you take infinite number of iterations, you are converging to the optimum, I suppose?
No, there's no guarantee on that it would reach the optimal, but because yeah, I mean, but it's expected that because the projection step would be nothing if it is inside the solution set. So if it is inside the body, it does not project anywhere. So
okay,
and it can like there can be other dynamics of how it evolves, but it is known that for a certain eta, for a certain learning rate, we can reach the optimal solutions. But or for a certain number of iterations and for a certain learning rate, we can reach the optimal solutions. But for a convex function, while the loss function that we're dealing with, or any neural network would be non-convex, would have some non-convex properties. So it's not guaranteed, but for a convex body, it is guaranteed.
Okay, that's interesting. And then how expensive is the iteration?
Yes, that's a good question. So here we are also dealing with the projection step. We are adding the projection step. So the projection should be efficient. And you can check out the paper. I don't think I have it in my slides, but projection operator is a cheap operation, or like we keep it as cheap as possible. It is theoretically correct, but it can be implemented in certain ways such that it's easier. It's fast, and it can find the optimal solutions faster. Yeah.
Thanks.
I have a question. Sorry, this is Junaid. So what is the alternative to randomly rounding? So why are you randomly rounding? And what does it do actually?
Yes, another good question. I think so this we have to do because graphs are discrete, while when we take a gradient step, we take a continuous step. So we add, let's say, 0.5 to each edge. We say the edge was 1, but now we add a perturbation which is 0.5. Instead of adding, let's say, 1 or 0, instead of flipping them in discrete steps, we take a gradient or we take a continuous step towards some direction. So in that case, we are making it a continuous, we are relaxing it to a continuous space. But the real attack would happen in discrete set. So we have to round it to the discrete graph space.
But you round it to the closest, right? Either 0 or 1. Why do you say randomly round?
So that is correct. But we should do like, let's say, 0 or 1. But randomized rounding is known to give like better. Randomized rounding would be with the probability of instead of considering rounding it like to the closest, let's say 0.5, less than 0.5 would be 0, or greater than 0.5 to be 1. Randomized rounding can give better guarantees. But in the paper, in the implementation, we actually do not. We do randomized rounding, but the performance is not different in rounding. That is correct.
That means the round function should take another randomization parameter, right? This is missing here.
Sorry?
The round function that takes P should also take a randomization parameter. Let's say it's like an epsilon that is 0.8, and you round based on that probability. So round should take another parameter for randomization.
So we rounded based on 0.5, if that makes sense.
But then if you make it 0.5, then what you are learning in the projection is not used at all. So you are why are you learning then if you are using 0.5?
We are not learning here, right? Anything?
But you are learning P. And then after you learn it in the rounding, if you use 0.5, that means whatever we learned, I don't care about it. Just give me 0 or give me 1 with 50% probability.
No. So I mean, 0.5 is the threshold. So P would be between 0 and 1. Any value
Yes.
from 0 and 1 for, yeah, I mean, for all the edges we have between 0 and 1. And if the Pij, let's say, Pij is less than 0.5, then we would call it 0. If Pij is greater than 1, greater than 0.5, we would say it is 1.
Okay.
Maybe let's forget about random part here.
I see. Okay. Thank you.
So that is one algorithm. That is a simple algorithm that we can consider. But this is not what we consider in the paper, I should note, because of various reasons. We can go into it, but I think we don't have much time. Oh yeah. So yeah, I mean, for simplicity, you can consider round to be greater than 0.51, less than 0.50, but in the paper, we actually consider a more a different kind of algorithm, which is known to give better guarantees for the discrete set. Okay, yeah, and similarly, like this method can also be used for online case, which I would not discuss in this presentation, but you can check out in the paper, or yeah, we can discuss if we have time. Okay, so that's the algorithm, and yeah, this is the broad pipeline that we follow. We have the original graphs. We use the 3D-PGD method and to find the perturbations at each timestamp while following the perturbation constraint that we proposed. And what we find is that the prediction would flip if we want to test whether the dynamic graph embedding modules that we have would flip the prediction while the embedding based anomaly detection would be evaded or would be fooled, and the embeddings and the graph snapshots remain. The evolution is preserved, basically. So if that happens, then we can actually conclude that these models are vulnerable to evolution-aware attacks, and which is alarming. Okay, and we've set up details what is the experimental setup we would follow is we consider these data sets, 2 different tasks, dynamic link prediction and node classification, and these 4 data sets, Rado's law, the email communication data sets, Rado's law and UCI, and the hyperlink network of Reddit. And then we also consider the DBLP co-author network for node classification. The baselines that we have, since there are no, the perturbation constraint that we have proposed is novel, there is no as such baselines, but we consider 3 different baselines based on existing works and other intuitions. So one is simple degree based. We consider top degree perturbations that such that they would satisfy the constraint, and then the random perturbations that satisfy. And another baseline that is competitive is the greedy baseline, where instead of taking this continuous step and taking a projection and all that, the projection gradient descent approach, we do a TGA, we do a greedy step. So we find the gradient, largest drop in the gradient, and we take the top k perturbations from this drop in the gradient, and we select them as the perturbations. Okay. So these are the baselines and data sets. Let's see the results. What we find is that our proposed attack is better than these baselines and is actually able to drop the performance of these models significantly while satisfying the constraint. And for different epsilon values, so we in the perturbation constraint we have these epsilon values which denote how much we can what fraction of the change we can add perturbations, how much of the fraction we can add the perturbations. And we can see that for as low epsilon as 0.3, the drop in the performance can be as high as 80%. And for 90%, for 90% of the fraction of the edges, we can actually get around 100% drop. So this is actually alarming and shows the vulnerability of these models. But we should also, and we find similar results for different data sets. We should note that some models like GCLSTM and DISAT are actually more robust than models like evolve-GCM. As even for the same epsilon, we can get less drop in performance for these models compared to evolve-GCM.
Do you have some intuition why? Can you just go back one previous slide? Do you have some intuition why? The next slide, sorry. Is it the next slide? Yeah, this one, the middle, the UCI email one. Why the degree and the TGA apps? Is it the degree? Oh, sorry, the degree and the random for the UCI email pretty much exactly matches, or?
I don't know. Like I don't know exactly for this data set why that would be the case, but in general, random is not a weak baseline, is what we found, because at higher epsilons, all these baselines should actually be similar. All the non-optimizing baselines should be similar, because if we are adding 90% of or like a lot of, so 90% of the fraction or 0.9 fraction is actually adding a lot of edges. And in that case, even adding random edges can be very effective in some sense.
But the TGA epsilon seem to be generally the worst, right? Especially at the higher epsilon.
Maybe for DISAT, but like for other cases, it's
okay.
Good. Yeah. And that could be because of and I don't know. Maybe it's like because of the greedy how it's like optimizing that. Yeah. But that is the case that if we increase the number of edges that we can add, for example, 0.3, 0.5, 0.7, 0.9 of the epsilons, the greedy kind of strategy is suboptimal because it cannot. It basically at higher because it's finding the highest gradient, but it's not able to strategize for the future. So it finds the highest gradient edge at each value, but it does not. Instead of finding all of them together, it finds one by one, and in that sense, it's not able to optimize for all of them together. When that optimization shows up when the number is actually very high.
I see. Thanks.
But
sorry, I have a question. So, which data set is this?
This one is an email data set.
Email data set. So, epsilon 0.9 means basically 90% of the matrix norm, right? The difference between the edges in matrices.
Yes.
So you change 90% of the edges in matrix, and the performance drops like 50%. Shouldn't it have destroyed the predictive model? What is like the performance in terms of accuracy, right? Prediction accuracy. So what is the performance to start with? What is the accuracy here?
So this is a link prediction accuracy. So let's say the accuracy was 90%. I think it was around 90%. I don't remember. But the original performance was 90%. And this is the relative drop. So this is
This is top one prediction.
top one prediction. Yes. I mean, the link prediction is actually just two classes. So I don't know.
So like destroying the matrix by 90% and the performance only drops 60%. That is a bit.
This is the relative drop.
Yes, but still, I mean, in for example, in adversarial graph neural networks, they change one or two edges and the performance dropped by 70%. And my second question is, what is the budget here exactly? For example, when we are talking about 0.10, which is like a good value actually, how many edges do you add or delete?
So that depends on the graphs, and that depends on the target that we are considering as well.
Yes, but do you know something like? Do you remember the values? 10% means, for example, thousands of edges, or maybe 10
No.
edges, or
No. So these are all targeted attacks. So this is maybe I do not specify that, but the prediction here is for a particular node. So here when we are talking about the change in the perturbation, change in the attacks, or change in
edges
the
of the node. You are changing edges of the node.
Yes, it's edges directly connected with the nodes. So that
Okay,
is not
so
too much.
it depends on average degree then. You are changing a fraction of the average degree. That makes sense. So 90% means not much maybe. You are not changing that much maybe.
Yeah. That's correct.
Okay, thank you.
Mhm. Okay. Yeah. And similarly, the results are hold for online setting as well. And yeah, I mean, mostly. So for dissect, that we see that TDPGT is not able to optimize that well. And that is also because how the optimization has become different now. And
Performance actually increases, which is a little bit interesting. Does it mean the performance? Yeah, for the dissect, the performance actually increases, so it makes the model more robust, I guess.
Yes, and actually, like it's a different objective. So because we do not have the future, at each step we are optimizing something, and that is not aligning with the future in some sense. For this case, yeah. I think this is okay. Okay, it's for Redus law.
And the reading group is ending at the 4 minutes. So if you a very good time to wrap up.
Yes. And just the final experiment I will show here. Yes, so this is against anomaly detection. Like we have a lot of anomaly detectors. We considered two in this paper, Network and Dynchain. And what we did was we found whether the perturbations were detected by these detectors or not. And to do that, what we did was we found these anomalous scores returned by these models before and after the perturbation between the two node pairs, and we found whether the anomalous score increased after the perturbation, or whether there is any difference between the two anomalous scores using a t-test. And what we found was that for these epsilon values, the perturbations were not different than, or the perturbed edges were not different than the unperturbed edges, and the anomalous scores were similar. So these are the, so to say, the allowed epsilons, and we can still find we can still see that the drop is significant. And similarly for Dynchain, we have these epsilon values, and yeah, there are other experiments as well. You can check out the paper for more. Okay, I guess in a nutshell, in this paper, I introduced this evolution-aware constraint and for discrete and dynamic graphs. And we show that it theoretically and empirically preserves the graph evolution. And an effective strategy using trajectory gradient descent can find the attacks under this constraint. And this has shown vulnerability of these SOTA models under the attacks which can be argued to be reasonable and realistic in the real world setting. Future directions can be like extensions to continuous time graphs and robustness against frequency-based detectors. So these detectors that I considered was only based on evolution and like the local perturbation should not be too much. There are also like frequency-based detectors which count the frequency of each edge in the history and say that if an edge comes which has a low frequency of coming in the history, then that edge can be acted as an anomaly. But in our work, we do not consider. We can add those edges. We are only concerned about the number of edges, not about the frequency, number of total edges that we add, or number of total edges we add at any time stem, instead of the frequency that we add, which edge we are adding. So we're not concerned about which edge, but the number of edges. Okay, that's it. Thank you for listening. These are the QR codes.
Yeah, thanks for the nice presentation, and there's a lot of interesting discussion for sure. Yeah, so happy to discuss more like offline about it. I think extending to continuous times is very interesting, but also highly non-trivial as well.
Yeah.
So I guess more on the site. Like, do you planning to go to NeurIPS this year? So maybe I will see you at the temporal graph workshop. If you
No, I think I have to skip this year. Yes.
Okay,
yeah.
okay.
Yeah,
But maybe see you in a future conference.
For sure, yeah.
But yeah, so thanks so much for the presentation. And if you have like some follow-up work about this or newer work on temporal graph, you can let me know, and then you can also share in the reading group.
Yeah.
Yeah, thanks for listening, everyone. And I hope you all have a nice week. Bye.
Thank you.
Thank you.